As we've taken a turn to more algebraic thinking and doing, a lot of algebraic doing, today we're going to have some geometric thinking, but then of course doing some algebra. Along the way though, we are going to have to think, and we're going to have to draw, and we're going to have to do a good job of following directions. I know that we sometimes struggle with that, right? This is kind of an exercise, and let's follow the steps, and if we do the things, then we'll get things right. But we're going to talk about similarity in triangles, all right? In right triangles first, and then in all other triangles second. And so with that, let's make sure that we do a good job of identifying the similarity, but follow those steps, follow the steps, follow the steps. So in lesson 4, here's really the explanation. Here's the theorem for our similarity in right triangles. We know that all right angles are congruent. We know that from our very first proofs assignment in chapter 1, lesson 6, 7, or 8, right around there somewhere. Now, the other situation is that our acute angles are complementary, all right? So if we have a big triangle where we have a right angle, I drew it at the top, and then we have these two acute angles, that means that if I cut this right angle in half, it would have to be that this is a right angle, that this angle is congruent to angle at B, and that this angle, this part of the right angle, would be congruent to this angle at A. It would have to be that way, that this angle is congruent here, and that this angle is congruent there, all right? If you have trouble understanding why that's true, then come see me, and we'll explain that differently or better. All right, but one of the things that we struggled with in the previous couple lessons is making sure that we orientated our triangles to face the same directions so that we could have the corresponding parts line up well. If we're not lining up those parts well, it makes it harder for you to write your fractions, to write your proportions, and then of course to solve for your variables. So we want to set you up for success, and so I want to encourage you to follow directions. All right, now with that in mind, some of our writing is going to look a little bit silly. So here again here's the actual theorem, theorem 7.4. I wanted to give you the heads up on that so that we are cool with that first. If I draw in this altitude from the hypotenuse to the right angle, if I draw in that altitude, right, altitudes are perpendicular, so I draw that perpendicular segment from the hypotenuse to the right angle, I am making congruent triangles where this angle here is congruent to that angle there, where this angle here is congruent to that angle there, and then of course we have our right angles, right? This right angle is not drawn, but you know it's there. So, with that in mind, we have these congruent triangles, triangle CAB, triangle DAC, and triangle DCB. We want to do a good job of drawing these triangles. So we're going to reorient those triangles so that we can see the large, the small, and the medium triangle, all right? So I'm going to tilt these all so that A is at the top, all right? So the double marked angle is at the top. So the double marked angle is at the top. That is not how you have to do it on your paper. In fact, you might want to draw it differently so that it's a little bit skinnier. It's just going to use less space on the horizontal. So in the big picture, we've got triangle A, C, and B. This is the big triangle, right? This is our big triangle. Our medium triangle is this guy right here. This is the middle triangle. All right, and here D is the right angle, and then C is where it's marked double, and then B is where it's marked single. For this guy right here, A is again at the top, D is our vertex, is our right angle, and then C is where our tiny angle, our one marked angle is located. So why that's important to do for the small one, why that's important to do for all these is so that you can compare how these triangles relate to one another, all right? How these triangles relate to one another. If I'm comparing the big triangle to the small triangle, I know that this hypotenuse goes with that hypotenuse. I know that this longer leg goes with this longer leg, and I know that this shorter leg goes with that shorter leg. All right, so we can see that extended proportion. We can also compare that big triangle to the middle triangle. All right, so AB goes with CB, and BC goes with BD, etc. And then we can compare these two, the middle and the small. Now, seeing all these letters written, it's not necessarily helpful. But what is helpful, if I tell you that this is X and this is 12 and whatever those are going to be, then we can create proportions, understanding, hey, this side goes to this side, this hypotenuse goes to that hypotenuse. It helps you write your proportions a whole lot easier. Again, this might not be helpful right now. Get it in your notes, it's part of the notes. But these pictures are what's key. If you do not have the pictures, it's going to be quite a struggle. So here we have a situation where I've got a drawing, and we're going to try to figure out what x is and what y is. There's a couple things to be aware of. All right, and the first is, let's see if we can redraw these triangles and label them. The secret is not the sides. I know that you want to focus on the sides. The secret is the angles. This angle goes with that angle. Double and double. Make sure we've got those. All right, so when I draw the big triangle and the medium triangle and the small triangle, all right, I have the single, double. I don't have to label anything yet. I want to draw and mark the angles first. In the big triangle, I do not know the long leg, but I do know that this is x. I know that the hypotenuse is, add them together, 16. In this medium triangle, I know the long leg is 12. I know the shorter leg, opposite from the single marked angle, is y. And the hypotenuse, I don't know what it is. Womp womp. Over here, in the little guy, I know the hypotenuse, I know the short leg, and I know the long leg. All right? Now, again, the long leg is opposite the double mark, opposite the double, opposite the double. The hypotenuse is opposite the right angle, and then the shorter leg is opposite the single mark. All right? So if you're doing a good job of marking the triangle in the original and in your drawings, then you should be able to identify where these are. You're using opposite sides, though. Single mark, opposite from the single mark is 4. Opposite from the double mark is y. Now, we've got two things going on. First of all, for y's, we're going to say that 12 and y are proportional in the same way that y and 4 are proportional. 12 goes to y goes to 4. That's one of my equations. For x's, I'm going to use these. X goes to 16, and 4 goes to x. It really doesn't matter if you say 16 goes to x and x goes to 4. It's going to work itself out. All right? So I don't want to be super concerned about that. But if we're using our cross product property, we get 12 times 4 is equal to y times y. Now here is where our Algebra 1 skills come in handy, because this gives us 48, and this gives us y squared. And so to solve this, we need to take the square root of 48 to get what y is. All right? In Algebra 1, we had to do plus or minus square root. We're not going to have a negative output here, so we don't need the negative square root. We just need the principal square root. The question is, do you remember how to simplify your square roots? So if y is equal to the square root of 48, hopefully you know that that is the square root of 16 times 3, which is going to be 4 times the square root of 3. All right? Now, you should be able to get that far. Hopefully you know from Algebra 1, Chapter 11, how to simplify square roots. We're going to practice that. Don't be alarmed. Don't be like, well, Mr. Edwards said I need to know this and I don't know. You're going to be fine. X times x, x squared. 16 times 4, 64. Take the square root on both sides. We don't need positive, negative, because we're not going to have a negative side length here. X is equal to 8. All right. Now that one is a little bit easier because it was a perfect square. Taking the square root of 64 is easy. All right. Taking the square root of 48, ooh, that's why you didn't learn that until Algebra 1. You knew this in elementary school. You learned this in Algebra 1. All right, how to handle that. So finding those lengths is a bit challenging. I want for you to try this one. If you get hung up on the radical, or on any radicals here, write what the square root is of, get that far, and then we will practice simplifying that square root in class. Draw your diagrams, label your angles, and then label your sides. If you're going to try to label the sides without labeling the angles, you are not going to be very successful. Maybe you surprise me, but let's try not to surprise me. Let's try to follow directions. All right, here is the other. All right, so that was right triangles. This is the 7-5 part, which is the side splitter theorem. Basically, if we draw a segment parallel to one of the sides of the triangle, we will cut those sides proportionally. All right, meaning that the length of CD to the length of CA is going to equal the length of CE to the length of the whole CB. All right, that's the first thing to know. Also, here, these ED and AB are also going to be proportional. All right, so that's the side splitter theorem. And there's a little caveat there where there's an extension to that, which says that this part is proportional to that part, that AD to DC is proportional to EB to EC, where this over that equals this part over that part. Now, it's not equal to this over this because this is the whole thing. So if you're going to do the part over the whole, that's different than the part over the part. right? The part over the whole is different than the part over the part. So be aware of that and be careful with that. But these are similar triangles by angle-angle similarity. All right, so in this case, there's a couple ways we could do this. We could do this as 16 over the whole thing, 16 plus x, is equal to 10 over the whole thing, 10 plus 5. All right, this is thinking about it as, well, these angles are congruent and those angles are congruent. So by angle-angle similarity, this triangle is similar to that triangle. The total length here is x plus 16. And maybe you don't like 16 plus x, so maybe write it as x plus 16. It doesn't matter to me, I don't care how you write it. But for these, in order to solve these proportions, we're going to have to do some cross multiplying, all right? So this is 10 plus 5 is 15. 16 times 15 is going to be 240. Let me make sure I do that right. So 15 times 16 is 240. Okay, so 16 times 10 plus 5 is 240. And then 10 times x plus 16, all right, that might be, let me write this as 16 times 15, 240. Here, we're going to have 10x and 160, all right, distribution. We're going to have to subtract 160 and then divide by 10. That is one way that we could do this. All right, but hopefully you're noticing that, hey, Mr. Hibbett, you told me that other way, where we could simply take 16 over x is equal to 10 over 5. And so I can recognize that this is doubled to 10, this is going to be doubled, so it's going to be 8. Like I can do that without doing all the solving. 16 times 5 is 80, x times 10 is 10x, so 8 is equal to x. Either way, you're going to find out that 8 is equal to x. All right, sorry for the handwriting over there, I know it got a little gross. The side splitter theorem, all right? Either way you want to do it will work. I recommend this, but sometimes this is just quicker and healthier. All right, corollary, if we have multiple segments drawn parallel to each other through a series of transversal, then all of the parts are similar. This will be similar, proportional to that, just like this one will be proportional to that. So A over B will equal, AB over BC is going to equal DE over EF. So basically, if three parallel lines or more intersect two transversals, then the segments that they cut off are proportional to each other. Right? This one's a fun one, and I don't have an example in there, but we will reference this. It's basically the same thing that we just did here, except what if there was another parallel segment in there? Like, how would that change things? Well, not really. It wouldn't really change things at all. We would still have proportional cuts. This would be proportional to that, just like this is proportional to that. So we'd create that equation and cross multiply to solve. We'll do some examples like that in class. All right, theorem 7.7, the angle bisector theorem. So if we cut an angle in a triangle, it will cut the opposite side proportionally. Now this is a little bit strange, but basically this length over that length is going to be the same proportion as this length over that length. This one's weird because it's not similar triangles. All right, it's not similar triangles. But AC over CD is going to be the same as AB over BD. So there's kind of two ways to write that. This is proportional to that, like this part is proportional to that part, or this over that equals this over that. All right, so I've got both of them written, because again, rules of, if you just swap these, right? If you're just swapping those, that numerator for that denominator, it's the same proportion, right? Those are rules of proportion from kind of your pre-algebra. All right, so with that, again, let's make this as easy as possible, right? If this angle is bisected, then that means that 10 over 6 is going to equal 12 over x. 10 over 6 equals 12 over x. Cross multiply to solve. 10x is equal to 72, so x is equal to 7.2. All right? Hopefully we can just quickly do that computation. And hopefully it's not super challenging. It's not going to mess with us too poorly, but it should set us up for, hopefully, success. All right? The goal here is that you will be able to identify similarity within triangles. So we have the side splitter, we've got the angle bisector, and then we've got similarity in right triangles. Draw those right triangles. That's the secret. If you're not doing it, it's going to be a struggle.